which is classification of signals. Already we have seen one classification, which was basically dividing the group of signals into two categories. One is energy and power. Energy signal and power signal. Okay, energy signals are those signals when you calculate the energy, we will get the finite value. Okay, so energy expression is energy of a signal x of t is equal to integral minus infinity to plus infinity x of t modulus square dt. So if this quantity is not infinite, if it is finite, so let me denote it like this. So this is infinity. Okay, if it is a finite quantity, we call such signals as energy signals. But if this turns out to be infinity, then you can go and evaluate power of signal, which is limit t tends to infinity 1 by t integral from minus t by 2 to plus t by 2 modulus of x of t whole square dt. And if this turns to be less than infinity, then we call it as power signal. Okay, so this is the condition for energy signal. Now if you evaluate the energy and it turns out to be infinity, then you go and evaluate the power, and if it is finite, non-zero, then we have what is called the power signal. Now there are signals in which neither energy nor power is finite, so such signals can't be put in this category. Okay, so that is neither energy nor power signal. Next classification, we have done a lot of examples, that's why I am not going much into it again. Next is analog and digital signal. Analog and digital signal. Okay, analog and digital signal. So what is analog and digital signal? We need to look at the amplitude of the signal to say whether it is analog or digital. So we have a time axis, which is the independent variable, and then we have the x axis, which is the independent variable, and y axis, which is the amplitude of the signal. So say x of t. So the amplitude of x vary in some fashion like this. Okay, now all that you need to check is whether this signal is allowed to take any value in a given range. So usually signal variation has some kind of range. Okay, and within that range, whether all values are permitted for the signal to take. Okay, so such signals are said to be analog signal. When do we say that a signal is said to be digital? If the amplitude of the signal is restricted to some discrete levels. Okay, so like this. So this is one level, and then this is another level, this is another level, and the number of levels could be any number. It is not necessarily 2, so it will be, say, level 0, level 1. Okay, so 0, 1, 2, 3, 4, etc. So if it is if the amplitude is allowed to take only values which are restricted to these levels, then we will say that this is a digital signal. Okay, we are not saying anything about the independent axis when we say a signal is analog or a digital. Okay, so for example, if I draw a signal, okay, so this is an example of a digital signal. So here this is analog, this is digital. Okay, this difference you need to know how to say whether a signal is analog or digital. You need to look at the y-axis, the amplitude, the value which the signal would take. Okay, So this is also x of t. A third classification is into continuous time, and discrete time. Continuous time and discrete time signal. Okay, as the word time enter into this definition or the name of the category, so you can understand that we are not talking about the amplitude of the signal here, we are talking about the independent variable t. So if the signal is allowed to take or if the signal is defined for all values of time, so it could be a digital signal also, like, so we have a digital signal. Purposefully taking this example of a digital signal. So digital signals are restricted in amplitude, but when do we say that it is discrete time also? Okay, so this is a continuous time signal. Okay, this is our time axis. But you see that you take any value of time, okay, any value of time in the x-axis, you take any point, the signal value is defined there. Okay, it is not restricted to some discrete instance of time, but all values of time, for all values of time the signal is defined. So let me just give that definition here. A signal is said to be continuous time if for all instance of time the signal value is well defined. Okay. For all instance of time, you take any time here in the time axis, there is no restriction. It is not like 1 second, 2 second, 3 second, anything between also 2.357 second also the signal is defined. Okay, so such signals are called continuous time signal. Now what is discrete time signal? A discrete time signal could be an analog signal also. So the picture here which I showed here, this is a digital signal but continuous time. So let me just write that. This is a this example is continuous time digital signal. This is continuous time digital signal. So why do I say digital signal? Because the amplitude of the signal is confined to certain levels. It is not taking any amplitude other than the levels which are predefined. Okay, it is not taking anything between these two levels. Okay, either this level or that level which is defined beforehand. So now let's look at an analog a discrete time analog signal. So for that let us draw another graph. Okay, so here I have an index. So this is my, I usually represent it with a square bracket. Whenever we represent discrete time signal, I use a square bracket and the index is n. So So the n can take values 0, 1, 2, 3, 4, 5, 6, 7, etc. And this is minus 1, and then minus 2, etc. So if you look at the signal is defined only for certain instance of time, okay, or not for all instance of time. So between 0 and 1 I don't have a definition or a value for the signal. It is undefined. After 1, then only 2, nothing between. Okay, so n is some index, and that basically tells you, so here n is an index which gives the instance at which the signal values are defined. Okay, so the discrete time signal are defined only for certain specific instance of time. Okay, so usually in practice what happens is that you have a continuous time signal which is naturally occurring, and then what we take is we take the sample of those signal at some intervals, okay, say delta t. So you can say that the interval between one sample and the next sample is delta t. Similarly between this sample and this sample also delta t. So all these intervals are basically delta t spaced. So the relation between the discrete time and the continuous time signal is that the t time axis is discretized. So t axis is discretized. So how is it related with this index? So basically the t is given as n into delta t, where delta t is the sampling interval. But we don't all the time carry around this delta t. So we could have, if you say that if this is the time axis, okay, then what we could do is that if this is a time axis, then what we would do is that this instant is basically delta t, this instant is basically 2 delta t, this is 3 delta t, etc. But it is really inconvenient to carry around this delta t all the time. So we suppress this delta t, and then instead of the t axis we define the n axis. Okay, and n takes values which are integers. Okay, it could be negative integer for negative time, positive integer for positive time. Now if you look at the y direction for this particular signal, I have not put any restriction to the values which the signal can take. So x of some index can take any amplitude. Okay, so therefore this is an analog signal. Okay, so this is an analog signal. So this example is basically a discrete time analog signal. So I just want you to really understand that discrete time doesn't mean digital. Discrete time means the time axis is discretized, whereas digital means the amplitude is discretized. Okay, so this is discrete time analog signal, and similarly the previous graph shows continuous time digital signal. Okay, because for all instance of time the signal is defined and the amplitude is limited to certain predefined values. Okay, so this is often a confusion with the students, so you need to be understanding what is what. Okay, another very important classification is periodic and non-periodic signal. So that is number 3. Number 4. periodic and non-periodic. So we have seen energy and power signal, and then we saw analog and digital, and then we saw discrete time, continuous time. Now this is number 4, periodic and a signal is said to be periodic. Signals are functions, and you know when is a function said to be periodic. So same is the definition. Said is said to be periodic if we can find t, which is basically called the period, such that x of, so let me say signal x of t is said to be periodic if we can find t, which is called period, such that x of t plus or minus capital T is equal to x of t. Okay, so let us take in this course we will restrict ourselves to analog signal, but we will do both continuous time and discrete time. Okay, in this course we will do one-dimensional continuous time signals and one-dimensional discrete time signal, but we are restricting ourselves to digital signal, analog signal. Okay, all the signals that we consider will be analog signal, but they could be either discrete time or continuous time. So let me define, or give some examples for this periodic signal. First of all, in continuous time. So for example, everybody knows that a sine omega 0 t. Okay, so this signal, so is it periodic? So if it has to be periodic, then as the condition requires, can we find a time such that when you replace t, so this is basically a shift operation which we have already seen. So check whether we can find any value of t. So it could be plus or minus. Can we find a t such that this is equal to sine omega 0 t? So this is the check that we need to do. So what is the requirement? So if I LHS, if I take and expand, so this is basically sine omega 0 t plus or minus omega 0 capital T. Now what is the requirement? If omega 0 into capital T is multiples of 2 pi, okay, multiples of 2 pi, so then so how do I write it? So if let me impose the condition, if omega 0 into capital T is some multiples of 2 pi, then what happens is that sine omega 0 t plus or minus k 2 pi we will get, and this is definitely equal to sine omega 0 t. Okay, so if you want to get, there is a condition, under certain condition we can say that this signal is periodic. Therefore we can say sine omega 0 t is periodic if omega 0 into capital T is equal to k into 2 pi. Or we can say that the period, or the condition is basically, therefore the condition is this, or let me say, therefore t, or the period, is basically 2 pi by omega 0. any integer multiples of 2 pi by omega 0, if you shift the signal you get the same signal. Okay, so it could be k could be where k is basically 1 or plus or minus 1, plus or minus 2, plus or minus 3, etc. So for any value of k in this you can get back the signal. Okay, so the answer is that this is a periodic signal and the period is basically given by this. Now when we say the period of the signal, it is the minimum shift. Okay, so here I said t is the period, but for this particular problem there are various values of t that satisfies. So does that mean that all of them are called period? No, the smallest shift that give back the signal, that is what we usually call as the period. Okay, so let me state that also. The smallest shift which give back the original signal is called the period of the signal. So that means in this case t is basically, it could be a left shift or a right shift. So depending upon whether you use a plus integer or minus integer, you will get left. But that is not, we are only interested in the magnitude when we talk about smallest shift, either plus to the left or to the right, which gives back the original signal. That is what we call as period. So in this case, therefore t is equal to 2 pi by omega 0. Okay, so if you graphically look at it, it is easy to see a sine wave. So this is a sine wave. It keeps on oscillating and it continues on, and this continues on to the left also. So this is our sine omega 0 t, and this is what we call as the period. This we have found that this is the shift. If you do to the left, it will come here, and it is the same. You can't distinguish between. So this is same as sine omega 0 t plus or minus capital T. You can't distinguish it. Okay. Any integer multiple of t also, capital T also, if you shift it, you will get back the original signal. So there is no way you can distinguish between the original signal and the shifted signal by the period, either to the left or to the right. So therefore, one thing is sure, that all periodic signal have infinite duration. Okay, that means it goes from minus infinity to plus infinity. So that is a common feature of all periodic signal. Okay, another note: all periodic signals extends from minus infinity to plus infinity. So that is the domain of the function. Okay, the domain of the function cannot be finite. It cannot be from say 0 to say some 5t or something like that. It's not possible, because when you shift it, you get something different. Okay, so all periodic function has to be infinite duration signal. Only then you can get back the original signal after shifting it. For example, do not confuse cases like this. So you have say a wave like this, to the right. Okay, so the right, it continues like this, but to the left it stops here. So there is everything is 0 here. Now the question is x of t periodic? Okay, so this is t, and this is also t, like this. This is also t. So it is repeating in the positive side, but it is 0 on the negative side. Okay, is this signal periodic? The answer is no. Why? Because if you shift it to the left, what you get, if you shift it by say x of t minus capital T, if you do it, what you get is this. So this is what we will get. So that means from 0 to t it is 0, whereas in the original signal 0 to t we have a square wave which is absent here. So the shifted version is not the same. So this is not equal to x of t. Similarly, if you shift to the left, same thing happens. So you will have like this. Okay, and here it is 0, but here it is repeating like this. So this signal is not, so this is basically x of t plus t shifted to the left, but here it is 0, whereas the original function up to 0 it is 0, but here it is 0 only up to minus t. So therefore this is also not equal to x of t. So you cannot have a periodic signal if the duration of the signal is where it is non-zero is really not extending from minus infinity to plus infinity. So this is a must condition, that all periodic signal extends from minus infinity to plus infinity. Another thing is that all the periodic signal are power signals. They cannot be energy signal, because the energy will be always infinite, because every period has some finite energy, and since it is repeating from minus infinity to plus infinity, it will have infinite energy. Okay, so that also you can note down. All periodic signals have infinite energy. They are power signals. Okay, they are power signals. Because, what is the reason? Because each period has finite energy, and therefore since it extends from minus infinity to plus infinity, there are infinite number of periods, and therefore finite energy multiplied with infinity will give you infinite energy. Alright, so that is another classification. Then okay, one more example I want to give in the case of a discrete time signal. So discrete time periodic signal example. So example of discrete time. So you can have combination of different discrete time periodics. Okay, and so let's say x of n. I said I will use this square bracket whenever I talk about discrete time signal, and the index is n, not t. But you know the relation between n and t. You need to multiply n with the sampling interval in order to get the t. But delta t is not really carried over in the definition. So we will only write x of n. So let's say x of n is equal to e raised to j omega 0 n. So this is the definition. Now the question is whether this signal is periodic. Okay, discrete time periodic signal. Okay, so I'll pose it as a question: is x of n a discrete time periodic signal, or let me further modify it, under what condition this signal can be periodic, discrete time periodic signal. So question is this: under what condition x of n is a discrete time periodic signal? So that is the question. So x of n is given as this. Now again, when you talk about discrete time signal, the requirement is that a discrete time signal is said to be periodic if you shift it by n samples, capital N samples. There capital N is the minimum value of the shift, so it could be a left shift or a right shift. Then you get back your original signal. Okay, because discrete time signal, not all values of time is defined, so you cannot shift by any value, you can only shift by integer number of samples. Okay, so if you want to get back this, so imposing this condition, so e raised to j some omega 0 into n plus or minus capital N is equal to x of n. So this is the condition for periodicity. Okay, which means that, so x of n is what? X of n is basically e raised to j omega 0 n, which means that e raised to j omega 0 capital N should be equal to 1. Should be equal to 1. Which means that, what does that mean? Which means that omega 0 into capital N should be a multiple of 2 pi. Omega 0 into capital N should be a integer multiple of 2 pi. Only then this condition be satisfied. Okay, so this is the condition. But if you further look into the condition, the exponent here should have an angle which is equal to multiples, integer multiples of 2 pi. Now n is an integer. N is an integer. So therefore, if you further look into the condition, then we say that omega 0 should be k into 2 pi by n. Okay, omega 0 should be k times 2 pi by n. N is an integer, and so therefore, so k by n is a ratio of 2 integer, and then it is multiplied by 2 pi. Now here there is a very interesting thing, that is, if omega 0 is something like say half or pi by 2 or something like that, can this be a periodic signal? Can it satisfy this condition? Okay, so if omega 0 is something like say p by q form, so if omega 0 can be expressed as p by q. P by q means what? A rational number, right? All rational numbers can be expressed in p by q form. So where p is an integer, q is an integer. So that is what we mean by it. So if omega 0 is is a rational number, so let me write rational number, then it could be expressed in p by q form. In such case, the above condition can never be satisfied. This condition can never be satisfied. Then the above condition can never be satisfied. Why? Because on the right side we have pi, which is an irrational number. Satisfied because pi is an irrational number. That's the reason. Okay, because pi is an irrational number, we cannot satisfy this condition if omega 0 is a rational number. Okay, so the frequency cannot be a rational number. This was not a restriction for continuous time, but this became a restriction only for discrete time. So therefore for periodic discrete time signal, omega 0 should be a multiple of pi. Should be a multiple of pi. So let's now look at some example of this kind. So I said e raised to j omega 0. Omega 0, if I write it as say n by 6, this is non-periodic. Okay, whereas e raised to j pi by 6n is periodic. Why? Because I have pi by 6 which is omega 0 into n, some n. I can find out now the n also is equal to k times 2 pi by what was our condition? 2 pi by n is equal to omega. Okay, so omega 0 is equal to, okay, k into 2 pi. Into 2 pi. Okay, so therefore this pi will get cancelled because omega is pi by 6, which is a multiple of pi, and which means that our n is equal to so the smallest value which k can take is 1, so n is equal to 2 into 6, which is 12. Okay, so you have to take k such that we will get the smallest value of n. So k has to be an integer. This has to be an integer. Okay, it could be like plus or minus 1, plus or minus 2. To find the period, you can take all the plus values, okay, because minus doesn't make any significance here. So 1, 2, 3, 4. So these are the values which n can take. So you have to take one value of k such that n become an integer, capital N become an integer, the smallest possible value. Okay, so if you shift this function by 12 samples, you will get back this function. So you can see that. So e raised to j pi by 6 into n plus 12. So what will happen? E raised to j pi by 6 n then plus, then 12 by 6 is 2 pi. So this is equal to e raised to j pi by 6 n into e raised to j 2 pi. So this is basically 1. So this is e raised to j pi by 6 n. So we get back the original function, okay, which is our x of n. But this was not possible for e raised to j n by 6, because here omega is basically, for this example, omega is basically 1 by 6. It is a rational number. So if it is a rational number, it is never possible to find a relationship satisfying the above condition because pi will never get cancelled. So n you can never get as an integer. Okay. So I can also invert this relationship and write n. So n is basically k into 2 pi by omega 0. So if I try to apply that formula, so what will happen? So n I am trying to find out. So k, then 2 pi, and here omega 0 is 1 by 6, right? So 1 and 6 goes here, so it is equal to k into 12 pi. Now this 12 pi or k into 12 pi, no matter what k you take, you will never get, cannot be not an integer. Okay, is not an integer, so therefore it cannot be periodic. Okay, pi is an irrational number, so therefore you cannot, if it could be expressed as a p by q form, then you can always find a k such that the denominator will cancel and you will get a integer value for n. Okay, but here it is impossible to find any period, and therefore if you can't find a period, then it is non-periodic. I hope this is clear. If you have any doubt, you should ask. Okay, one more example I want to take. So this time again going back to continuous time periodic. Okay, example say 3. So x of t is equal to sine 3t plus sine 4t. So this is continuous time signal. You see that my omega here, so this is omega 1 is equal to 3, and here omega 2 is equal to 4. This is continuous time signal, and it is not a multiple of pi, or so can it be a periodic signal? For continuous time signal, this is not a restriction. So only thing we need to find out is find the period of each signal. Okay, so the first signal has a period, so t is equal to 2 pi by omega 1, so that is your t1, so that is 2 pi by 3, and similarly t2 is equal to 2 pi by omega 2, which is equal to 2 pi by 4, or you can write even as pi by 2. Now what is the period of the sum of the two signal? Okay, so find the period of x of t. So it has two components, two sine wave we are adding together. The first one has a period 2 pi by 3, and the second one we have a period equal to say 2 pi by 4. Okay, so if you look at graphically, you will get it quickly. So sin 3t means if you take a variation of 2 pi, 4 pi, then 6 pi, etc. So sin 3t means if I plot, there will be basically 3 cycles in 1 2 pi. So if I have to draw this roughly, so this is how sin 3t will look like. 1 cycle, 2 cycle, 3 cycle. Okay, so in 2 pi we will get, so again this repeats. Okay, so I am drawing a rough sketch. Now sin 4t, how does it look like? We will have 4 cycle instead of 3 cycle. We will have 4 cycle. So let me use a different color for this. So like this. Okay, 40. 2 pi, if I have 4 cycles I have. Okay, so then what is the period of, so what we found out is that the period of the first signal is like this. So this is our T1, which is 2 pi by 3, and the period of the second signal is little less, and this is your T2. So we are adding them together, and then what is the period of the signal, okay, or what is the smallest value what is the smallest value of time after which you have both of them coming together. So definitely you can see that at 2 pi they become both 0 at the same time. So just like it is at t equal to 0 and t is equal to 2 pi, also you have both of them coming together. So how can we get this? So the way to get is basically, if you take so if this is T1 and this is T2, and you need to look for the common multiple, right? Common multiple, the least common multiple of T1 and T2. So the period is basically LCM of T1 comma T2. Okay, so what is the LCM of T1 comma T2? So you have to write the multiple of T1. Okay, so T1 multiple. So you have T1 is basically 2 pi by 3. So 2 pi by 3, then 2 times that, 4 pi by 3, then what? Then 3 into 2 pi by 3, which is basically 2 pi, and then 4 into 2 pi by 3, that is 8 pi by 3, etc. So this is basically the n integer multiple of T1, and similarly integer multiple of T2 I can take. So what is T2? T2 is pi by 2, so it is pi by 2, and then I have 2 pi by 2, which is pi, then I have 3 pi by 2, then I have 4 pi by 2, which is 2 pi, etc. So now you can see that 2 pi is the least common multiple. So just like you have studied in school how to find LCM. So if you have T1 and T2, just find LCM, and that will give you the period. The period of the sum of the signal is 2 pi. So I hope that is clear. So if you have a 2 sine wave, then you can find the individual period. So you know the omega, you can find the individual period T1 from omega 1, which is equal to 2 pi by omega 1, and similarly 2 pi by omega 2, and then you take LCM of T1 and T2. Okay. Now one thing you need to be careful about is that another example number 4, say x of t is equal to sine say 3t plus sine pi t. The question is the signal or periodic? Not can the signal be periodic, is the signal periodic? Because I have given omega 1, omega 2 in the expression, is the signal periodic? So we may think like I can maybe follow the former approach. So I will find T1. So T1 is basically 2 pi by omega 1, which is 3, and then T2 is equal to 2 pi by omega 2, which is pi. So that is, I will get 2. And then I got T1 and T2. So as before, I would say that so we are adding 2 sine wave, and each sine wave has different periods, and therefore the total period is basically the LCM of T1 and T2. So I will try to proceed and find out the LCM of 2 pi by 3 and 2. And what is going to happen is that you will not have any LCM. Okay, or you can say that the LCM is infinity. Why? Because this is a irrational number and this one is a rational number, right? 2 is a rational number, whereas 2 by 3 pi is basically irrational number. So you cannot have an LCM, or you can't have a finite LCM. Here we cannot find a finite LCM between a rational and irrational number. It is just impossible. Okay, so therefore conclusion is that though individual signals are periodic, the sum of these two sine waves are not periodic. Therefore the given signal is non-periodic. This is a very special case. One more example, example 4. X of t is equal to sine pi by 6t plus cos 3 pi by 2 t. Okay, so here I am trying to proceed in the same manner. T1 is basically 2 pi by 6, which is equal to so pi cancel, so this is basically 12, and then T2 is 2 pi divided by 3 pi by 2, so that is equal to pi cancel, and I have 4 by 3. Okay, and then I have T is equal to LCM of 12 and 4 by 3. I have no problem, both are rational numbers, so the LCM, as you can see, that it is 12 itself. Okay, so first multiple is 12 here, 4 by 3, then 2 4 by 3, 3 4 by 3, and if you continue like that, you will finally come to 12. Okay, so we have seen various cases, some of the cases when the sum is resulting in a periodic signal, and only one case if one of them is a multiple, one omega is a multiple of pi and another omega is basically not a multiple of pi, then such cases we will not have periodic signal. Okay, because we can't find the LCM of a rational and irrational number. But if both of them are omegas are rational, there is no issue. Both of them are irrational, then also there is no issue. But you can't have one rational and one irrational omega or time period. Okay, so that is the different cases. And discrete time cases has an additional complication. The period can only be an integer. Okay, capital N can only, because the shift can only be done by discrete number of samples, and therefore it can only be an integer. Therefore it insists that your omega in the discrete time signal should be an irrational number. Okay, so that pi will get cancelled when you take 2 pi by omega naught, and you can get for some value of k you can get a integer value for n. Okay, so I will stop here. We'll come back again after 5 minutes.